Come on, computer, don't give up on me now. I'm actually here for this class. Okay.
Give a sense fear.
I don't know if I'm afraid of it. I think I'm just more annoyed. But maybe it senses annoyance too. Okay, when we come up here, let's see. Normal trig, we plug in angles and we get out ratios of sides. Normal trig, we plug in angles, we get out ratios. Inverse trig, it's all backwards. We're plugging in ratios. And that's exactly what goes down here in the fill in the blanks. Given for inverse trig, given the inputs are values, aka ratios of sides. So given values, aka given ratios of sides. Inverse trig says, no, we find angles. Because, I mean, that makes sense. Inverse functions, everything's backwards, right? So plug in ratios, get out angles, whereas normal trig says, give me angles, I'll give you ratios. And by ratios, I mean like Sokotoa and Shoshikawa, right? I mean like Sokotoa and Shoshikawa.
What's that?
It was Anthony.
Oh.
Lexi's not here today. Oh. Coming back. So pre-cal. These could have been pre-cal problems, and once again, you don't have to have it perfectly down, but it might come up. Ratio. My S turned weird, and I just kind of went with it and didn't make it pretty. Ratios of sides. Over here, if the equation says tangent of theta equals -1, cosine of theta equals 1/2. Wait a minute, thetas. It's been a while. Hi, thetas. Why are there thetas in here? What do they represent?
X.
I mean, angles. Yeah. So we're trying to figure out who theta is for each of these. Who are thetas? Who are the right angles where tangent is -1? So Sokotoa, Joshikao. Tangent is what kind of ratio? Good. So opposite over adjacent. The only way for an opposite over an adjacent to be 1 is if they're the exact same thing and they reduce. Wait a minute, what angles in the unit circle? For what angles are cosine and sine, x's and y's the same thing? 45?
Pi over 4?
But careful, the over 2's are going to have 0's and 1's. We're going to get messed up. But pi over 4's have root 2 over 2's, root 2 over 2's. They cancel out. They reduce, technically. So the pi over 4's, but wait. I need the pi over 4's where the signs are opposite, because I need one to be a positive, one to be a negative for this division to get me a negative. What quadrants are the signs opposite?
Second and fourth.
Second and fourth. So I know my answers are going to be located here at 3 pi over 4, and here at, let's see, 8 pi over 4 minus 1, 7 pi over 4. But wait, couldn't I just say negative pi over 4?
Yes.
Go team. So for this first one, I could say, technically it's review, I guess I should be writing in green. Negative pi over 4 plus pi n. Bloop, 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 bloop. One equation for 2 locations. Wait a minute, huh? I thought we needed here and here or here, fourth or second. How does this work for both? Pi n. If I go pi from here, what quadrant am I in? There. Pi from there, I'm in here. I can just go by pi's. 1 pi, 2 pi. Well, sorry, 1 pi, 2 pi, 3 pi, or -1 pi, -2 pi. Technical notation. These n's are within a z, kind of like the double R back there for real numbers. Z means all integers. Integers are those positive and negative counting numbers. So you would have to go whole quantities of pi, a whole pi, another whole pi, another whole pi, or a negative pi. Anyway, but you would get both locations. I'm going from angles to ratio. No, I'm going from ratios to angles. Okay, how about this guy? When is the x1/2? That's the little one.
Pi over 6.
Careful. Pi over 6 is root 3 over 2. 1/2 is pi over 3. And I need it to be a positive, so, oh, that's easy. First quadrant is positive, but where else is cosine positive? Fourth quadrant. Because cosine is the x, and so positive can go up or down. Positive x. Okay, so I have this one. This one's a little different. I don't have like the same amount between each of the angles. I can't just put like a, hey, it's pi no matter how you go. I can't do that over here. But what I can do, it's going to look a little bit weird, but not impossible. My theta is going to be plus or minus pi over 3. That gets me both locations, and then I'm just going to add all their coterminals. Now, remember, I said the point of this section is not you memorizing all this calculus stuff, pre-cal trig stuff that would have taken us, what, I don't know, a whole chapter to get. That's not the point. This is just something that might come up. Does that make sense? Wait a minute. Why are we doing trig if the point was trig inverse? Why were we doing trig if the point was trig inverse? What were we trying to get alone, guys?
The angle?
The angle or the theta. Question. How do I get rid of tangent to get to theta mathematically? Divide. Wrong.
Tangent.
Wrong. Guess what I'm teaching pre-cal right now?
Properties of
Pre-cal. Logarithms. Okay. What if you saw something like this? Log base 7 of x equals 2. How do you get rid of the log? Divide it. No.
Base of 7.
Right. You have to do the inverse operation. I only do division when there's multiplication. And I had to drill this into their minds. I'm like, is it log of or log times? Because there are always people that are like, hey, just divide by the LOG. But here's the problem. What does that mean? Nothing. It's gibberish. There's no meaning to a log without an argument. It's like, ready? And I'm not making fun of you. This is something that happens every year in calculuses and pre-calculuses and algebras and all over the place. What if I was to do something like this? Okay, that's silly. Maybe I shouldn't have done like that. I should have done this. There we go. Okay. How do you solve for x? Divide by the square root. No, you know that it's not square root times. You know that it's square root of. You know this one, right? And if you go to your calculator, do you guys know that the square root is located right above the squared? Do you know why? Because they're inverses of each other. Do you know what's located right above the log, the common log, or the ln? The inverse, 10 to the, or e to the. Why? It's the inverse. How do we undo? You guys were right, right? We undo logarithms by raising to exponents. We undo square roots by squaring. We undo tangents by tangent inverse. The only way to undo. And what you do to one side, you do to the other. So guess what this is? Tan inverse, or inverse tan of -1. That's what we found. And what's this? Ha 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 ha. Cosine inverse. That joke's been made.
How would you write tangent?
That's why on last year's sweatshirt they had a little tangent graph on their TI graphing calculator for Joe.
Yes. And that graph is not even correct.
Cosine inverse of, it was the best that the graphic designer could do.
Okay. The graph is like overlapping with some reason. I'm like, where's the verb asking code? Like, not there.
It's the best they could do with the verb. But it has the right shape.
On our sweatshirts, we should all have on the back of our sweatshirts our names but in the math term. Hi.
Why don't we just convert binary?
That only works for I know, I saw people get creative.
Be creative, guys. Figure out math. You almost could.
Math can be my name.
I mean, I did my iHeart math back there. Because I just throw in Greek letters and make it look funny.
Because the first thing is I. Okay, that's
Hi. Wait.
Yes.
Yeah, it is I.
Tyzilla. I don't get it.
No, we right.
And that's a word. That's a blank word.
It doesn't really mean anything. I just threw in Greek letters
I
and
love math.
imaginary numbers and stuff like that. Whoa, we still have to do calculus. Guys, hold on. Whoa. But, good thought. Put as an example and be like, guys, like this. And then they're like, yay, let's do it. And then like, yeah, I'll send it in. Okay. We are supposed to take a derivative of an inverse sign. Wait a minute. Can you guys look back in section 2.6a? The very first example that we did, solving an inverse derivative. Not the weird x cubed minus 4 over x1 we did yesterday. The one before. What was the very first example we did? Sines. And we were trying to find the derivative of sines inverse. Did we do it? Yes. Without any of this. But it took a lot of work and we had to have a point. We can't stop there. We have to go beyond, especially for trig. So here's the dealio. We've talked about Sogotoa Choshikao. Trig matches with ratios, and so in inverse we have ratios. We're going to angles. Let's talk about how to discover the derivative of sine inverse rule. Not just one, like the example from 2 days ago, but the rule. Okay. Have we, up to this point in this section of notes this year, have we talked about the rules to memorize yet? No. You took a picture of them yesterday. You know they're coming, but we haven't talked about them yet, right? So if I just said, go, you're like, unless you rewrote it to be. Well, how did I get that?
Inverse.
How do you undo an inverse? You use the other guy. Oh. And this, doesn't this look like an implicitly defined inverse anyway? Like the x's and y's are switched?
Yep.
Oh. Can we take this guy's derivative?
Yes.
Yes. This is like taking derivatives of inverses implicitly that we saw yesterday. Hey, we didn't know the rule to this guy, but I know this guy's rule. This is easy. What's the derivative of x? 1. What's the derivative of sine? Don't forget your dy dx.
dy dx u prime.
Oh wait, this wasn't bad at all. Hold on. So for me to find the derivative of sine inverse, all I have to do is find this guy's dy dx, the dy dx of the implicitly defined. Oh. Okay, so dy dx is equal to 1 over cosine of y. Ha! Dun 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 dun. Wait. Do you remember that picture that you took yesterday? Do you remember how every single one of those derivatives did not contain any trigonometry at all? So wait a minute. If it was really that easy, undoing the inverse, getting back to the original, taking an implicit derivative and saying, yay, then what on earth is this? Derivative of sine inverse of x would be 1 over the square root of 1 minus x squared times x prime. Oh, it's just 1. 1 over the square. That does not look like that at all.
Oh, this one.
But what is this in terms of?
1.
And what is this in terms of? U's, but x. So maybe they're the same thing? How do we know what they... Oh, I think we have to go back and ask ourselves, who's y? Back here at the very beginning, I mean in green, it's technically pre-calc. If this is an inverse, isn't this a ratio? And more specifically, sine inverse, isn't this an opposite over hypotenuse? Wait, how do I know x over 1? Well, guys, who is inside the inverse? X over an understood 1. Oh. I could take this, x, and I could put them in a right triangle and say, hey, so you're an opposite of somebody and you're a hypotenuse of somebody? Wait, what somebody? Well, that's the ratio. What's this? Just from that original expression, I know that x, and hence x over 1, is the opposite over hypotenuse sine SOHCAHTOA. So I could put the x in the opposite spot, 1 in the hypotenuse spot. Y has to be an angle. Put him in the angle spot. Oh, all I need to do, guys, is find cosine of y. What's cosine of this triangle? Adjacent, over hypotenuse. Why did I write the word adjacent, but I plugged in 1?
You don't know.
We don't know adjacent. But what do we know about any right triangle? Don't we know a squared plus b squared is c squared? Can't I solve for my adjacent using? So when I go to plug in, isn't cosine the same thing as? And so can't I be like, who are you? Oh, there you are. Plug him in, plug him in. And I end up with dy dx, hence the derivative of sine inverse, being a trig that's been solved for. 1 over square root 1 minus x squared. Dun, 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 dun. Where's u prime? Oh, u prime is 1. Dun, dun.
Okay, that's
So
complicated.
couldn't you just stop right there? Why do you have to keep If it's multiple choice, you have to keep going.
Well, the problem, yeah. If they ask you this in terms of x, they don't want.
Oh, okay.
But that's why we have a forever card. Forever. Number 17, 18, 19. Forever number. Boop, boop. Oh, he's not yellow. Undo. Forever number 19. Hey, what do we do with forevers?
Copy them.
Copy them. Write them down. Study them. Memorize them. And remember them. Forever number 19. Now I'm going to show you guys, as you write down these rules, because most of you took a picture, most of you did not write them down. As you write down the rules, I'm going to show you one more example that's a discovery. That's a discovery of how to take another trig inverses derivative. And then we'll compare it to the rules and we'll see which one we like better, memorizing the rules or discovering it every time. So play with those, and then you can just, if you want to write down this next one, you can. If you want to put your pencil down after you get the rules and just check it out, that's totally fine also. I'm going to take tangent. Implicitly defined inverse, I can take a derivative. I have to use my trig rules if I go this way. Oh, wrong way. Secant is 1 over cosine. Haha. I can flip cosine equals. I need cosine. I need a triangle. Okay, there's my angle. There's my. It's going to be an opposite over adjacent this time, guys, because it's TOA. Stink. I need a hypotenuse. Oh wait, Pythagorean theorem. 1 squared plus 2x squared, which is 4x squared, square rooted, is my hypotenuse. Jason. Got him.
That's too much.
square root squared cancels out. Wait a minute. And I just showed you this forever card, didn't I? What would the forever card have had me do up here at the very beginning?
Keep tan inverse.
Keep tan inverse because I can deal with tan inverse because there's a formula for tan inverse. Who's my u?
2x.
So, can I avoid this whole blah 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 by just saying that the derivative of tangent inverse of u is 1 over 1 plus u squared times prime.
What?
Is this a good card to memorize? But what is all of this showing you? There is trig. There are trig derivatives occurring behind the scenes in the implicit form. But that trig points us back to a triangle whose ratios we plug in, which is why you don't see any trig in terms of x versions of the derivative. But check it. This is all why this is true. But ultimately, are they asking you why when they give you this problem? Nope. They're just saying, what is it? And you're like, I have a formula. 1 over 1 plus u squared times, someone help Eric out, u prime. There he is. That was a lot easier. So you guys, play with a couple. Oh, we just did that one. I did that one both ways. Let's do it again. Play with a couple. You know what? We probably better play with this one together. Hold on. Pause. Let me come back. Let's play with one together. Using the rules. Using the rules. Using the rules. Come on, computer.
Come on, computers.
Using the rules. All right, according to the rules, guys, how do you take the sine inverse derivative or the derivative of sine inverse? The rule says d dx, good, sine inverse of u is 1 over
Square root of 1 minus 1 over
1 minus u squared all times u prime. Okay, who's my u?
1 over
1 over, no.
1
Yeah.
over x.
Yeah, it's whatever's inside, right? Okay. I think we
X
might
to the
have a
negative
complex
1 power.
fraction coming soon, but that's okay.
X to the negative 1.
I like that you're thinking of it as x to the negative 1, Joe.
It's easier.
I just don't think it's necessarily easier
Yeah.
when we go to plug in this nasty square root in a denominator. I think I want the actual u. But when is x to the negative 1 going to be nice?
U prime.
I could do a quotient
Negative
rule,
x.
or I could do a pop it down, pop it down. Can you just bring down negative 1, x to the negative 2? What's the struggle, guys? It's the struggle of the last test that you got back. What do you have to do now?
Match.
Make it match. You gotta simplify. There's no way they're gonna leave a complex fraction. So someone tell me something. PEMDAS would tell me to do what in simplifying? Parentheses, right? So negative 1 times 1, negative 1. I have this little x squared in front, and now I have a 1 minus 1 over x. What are your brains gonna want to do? Yay! Okay, he's not even underneath. He's not. Okay, no. But we do need to do something. So I have a complex fraction. Some of you have gotten really good at my complex fraction trick.
Multiply by
Multiply minus.
conjugate.
Yes and no? Conjugates are going to be nasty because there's no plus or minus outside the square root. I'm not sure I'd do a conjugate. I kind of like the idea of x squared, but if we do that, do you guys realize, isn't he not just an x squared? Isn't he a square root of an x squared? Well, it makes it a little bit nasty. But now that there's a square root, I can legally distribute him in. He's just chilling because he's his own little dude out here. And then he's just chilling with a negative square root of x squared.
Is that illegal to cancel out the square and the square root?
I can bring this guy in, so I'm going to have an x squared minus, and then, oh, those reduce. Whew, that's prettier. What's Tyler asking if she's saying, wait, isn't it legal to cancel out a, what does she see? Here's the struggle. Can you guys make this match with the final answer they would have? No, because you're like, why the heck did an absolute value come? What sign, not this, what sign, if I put in positives, negatives, squared and square root, what sign will this always have? Positive. What's this always going to have? Positive, anything squared. So a positive over a positive, I need it to always stay positive. Now, what Tyler said, or what she realized, was, hey, square and square, doesn't that cancel? Yes, except here's the dilemma. It cancels, but must stay positive. Now the negatives is chilling in front. He's there at the end too. But the x squared square rooted is technically an absolute value of x. And then these two can technically reduce, but when I reduce, an x could be positive or negative, so I have to maintain the meaning and throw in an absolute value. Always positive, I need the end result to always only be able to be a positive, or else I've messed it all up. I know it's weird, I know it's nasty. I said, wait. Doesn't that look like one of the derivative rules? Which one? Cosecant inverse. Do you guys remember way back when in pre-calc? You were given on the test something like this.
Oh.
But is there a second cosecant button in your calculator? No. And most of you, even on the test after I told you to study it and done sample problems and caught you on it before and said study, try so hard.
Wow.
You were like, wait, cosecant is 1 over sine inverse. No.
It's not cosecant.
It's sine. The way to do cosecant inverse was to use sine inverse and say the ratio needs to be the reciprocal. Oh my goodness, I could have way back here said that he was him and gone straight to his rule.
Conclusion. That's smart.
It doesn't usually happen, but this time it did. Anyway, that's kind of snazzy. Remember, how to do cosecant inverse, cotangent inverse, or secant inverse is to do the other inverse. It's reciprocal inverse of the reciprocal. Anyway, that's a pre-cal thing. Whew, let's do one that's easier. Can I? There you go. This one's easier because there's no fraction inside the inverse. Okay, we got this. All right, go for it. I did the hard one. I did the fraction-y, simplify the complex fraction one. Can you guys do this good old-fashioned? Wait, what am I gonna have to do? Product rule, go. Oh, come on. Anytime we learn new rules, we know that the old ones still apply, like chain rule, like product rule. I see a U with a U prime. But don't stress about that, just go product rule first.
Can we do that one?
Good. I'm not sure it's going to help though, because you're going to get ln of sine inverse, which is going to get nasty. See what I mean? Whereas if you just go for it right now, you're going to have a sine inverse, but the other guy just turns into a weird fraction anyway. Good thought, though. He was saying, can we bring in ln? Because you could do ln, and you could do a product property, and then ln of e. But then it makes this so much nastier. So I said it probably wasn't smart. I'm going to slowly start. Oh, that's right. The derivative of e to the x is e to the x. That's nice. Wait. 9x squared? 3x times 3x? 3x squared? Oh, u squared. The new rule for second, d first, derivative e to the x is e to the x. Plus first d, ooh, I need the rule. And the rule is 1 over the square root of 1 minus him squared, and 3x times 3x is 9x squared. Oh, times u prime. U prime. I'm getting out my nifty green pen because that is a symbol, if we're looking at derivatives, that we're supposed to ask ourselves, is there anything in common? Get them out of there. There is. A little something. Something.
We're making progress.
In some way, shape, or form. Some people would really want to kill a puppy right now. Are you going to?
No.
This is not 1 minus 3x.
You can't split it.
Stuck. Leave it.
If it's multiplication, you can, but it's not.
This is not a perfect square. I cannot square root and have anything cancel. No.
So that's just as far as you can go.
But the nice thing is, in a multiple choice question, you'd be looking at the answers to see that, oh, it matches, I'm good. Or if it's an odd, you would go to the back of the book and be like, oh, I'm done.
Did they change a little in multiple choice for that one? Sometime. Maybe they multiply e into it.
Yeah. Or have a 1 over instead of a 3 over, or have a 1 minus 3x squared instead of a 9x squared.
Okay. That's small distortion.
How about this guy?
Chain rule.
Yeah, and that's it, right? No product, no quotient. I have a rule. He's there. Go look at him. What's the derivative of tan inverse of u?
1 over 1 plus u squared.
1 over 1 plus
U prime. Right? So can't we just go plug in and chug in? Ooh, squared. Him. Squared. Scared. Yes, I'm worried about you guys memorizing your forevers and keeping them memorized and knowing how to plug into them and use them, but you know what? Most of the time, it's on you whether or not you do that. Memorize, you have to memorize. Remember, you have to memorize it so good that you don't forget. But what I'm more worried about is, would you kill a puppy or not? I'm more worried about you simplifying than anything else. If you memorize your forever cards. If you don't, well, we'll have words. But, do you remember how to FOIL a perfect square?
Yes.
You sure? Would you do squared? Double? Squared? Yay! Would you?
Yes.
Did you remember? No, that's not blue, that's not new, that's old. You could either make it a plus b times a plus b, or you could make it squared, double, squared. There are 3 pieces, not 2. So why is the final answer 1 over 2x squared plus 2x plus 1?
Because you add 1 and then you factor.
If you never know why, then see what you can do. Oh, 1 plus 1 is 2. Oh, look, I can pull out a 2. But then where did it go? Oh. Simplify. If you ever look at multiple choice answers, you're like, mine's not there. Oh, that one's close. Pause and rethink. Is there something else you could do to arrive at one of the ones that doesn't naturally match? Yeah, there was a.
That was me.
Yeah.
So, like, trying to think of my score. So, like, if it was multiple choice, keep going until you get as simplified as you can.
Well, I mean,
until, like,
to save
it
time,
matches
keep
the
an eye on the answers. But just because there's one that looks similar to yours in some form, some version, some state, doesn't mean it's the right one. Because there might be a little mistake, so you might need to keep going, so you have to keep aware of that.
Okay.
Yeah, you have to be careful.
But if that was like some sort of long answer, you like
Oh, you could have boxed it way back up here.
Yeah, okay.
You had to get into the rule, right? You had to get everything in, only in terms of x, no like dy, dx weirdness, but otherwise, yeah. Did you guys find this rule? You're plugging in. Are you getting a negative up top? Yeah, absolute value. And you're doing 5x times 5x is 25x. Would you have been able to make it match?
Kind of.
Wait, the 5's trapped inside an absolute value. I don't get it.
No, absolute value 5 is still 5, no matter
Absolute
what.
value 5 is still 5. Pulling the 5 out doesn't lose any meaning. I'm allowed to pull a constant out. Absolute value of 5 is 5. That's okay.
Right.
And then I just reduced.
That's it?
Oh, well, you better do the square root.
A squared minus b squared.
Exactly. Does not have a square root. So yes, that's it, Joe. No more. I was trying. There are a few of you that were like, okay. That's what your brain's going to tell you on the test, and you're supposed to say no. Wait, what's this?
You're not supposed to say anything.
Oh, slope. That just means that's easy. Whenever it says find slope, it means find the derivative.
You're not supposed to say anything else.
Tan negative 1.
Okay, arctan, good. It's the exact same thing as tan negative 1.
Yeah.
So I can think of this as x, wait, rewriting. Rewriting.
Homework to do tomorrow?
Because we're just doing tons of examples. We were done a while ago. As soon as you guys were done the forever guard, kind of. But it's only half of the section, right? So maybe it's not as long. 10 problems? 10 problems? You can do anything for 10, well, kind of problems. I applaud these class last night. You can do 5 minutes. No, not anything. Anyway, but 10 problems. You guys can do it. Second?
What can we do?
D first plus, try to plank it for 10 minutes, 5 minutes.
Someone in
Although there's one class that was like, they were up to 3 minutes and 30 seconds. And I was like, Second D first plus first D second. Okay guys, what would we have to be careful of in this one? Times U bunch. Right here. Right here. Don't forget your D. Oh, I have to make it look pretty? No. Why don't you just plug in your X, plug in your Y, and see what happens? Later, gators. Play around with your 10 problems. Do the best you can and come in tomorrow with questions. All you have to do is submit your All you have to do is submit your Bye guys. Why are we groaning?
We have an essay every